It's great pleasure for me to introduce our speaker for the week. It's our very own Adam Kaufman, who is of JILA and CU Boulder NIST. So Adam has earned a number of awards and honors, but I'll just highlight a couple here. So he was the 2016 DAMOP Thesis Prize winner, and he also recently just was awarded a 2020 ONR YIP. In addition to that, you probably all know that Adam was one of the founders and is one of the main organizers of this VAMOS seminar series. So with that, I'll turn it over to Adam. Go ahead and give your talk.
All right, you guys can hear me all right?
Yes, we can.
Cool, all right, sounds good. Shimon, thanks for the introduction. Just so everyone knows, I blame Shimon and Monica for roping me into giving one of these earlier talks, but I'm happy to do it. So I'll be telling you about recent work that's been coming out of my lab at JILA, focusing on controlling arrays of strontium atoms in optical tweezers. Broadly, the focus of the work that's done in my group is really looking at microscopically controlled quantum systems. By which I mean really having a system in which you can control the constituents at the level of individual quanta. So this kind of capability is really central in quantum science in general. It's useful for quantum communication, for studies of many-body quantum systems at a single particle level. It's quite fundamental to quantum computing, where it's key that we have the ability to perform single and 2-qubit gates. One focus of this field in general has been learning how to apply the capabilities that we've developed on a few qubit scale and expand them to much larger system sizes. So really combining scalability and control. And one theme that will come out of this talk is looking at how these kinds of ideas might also be relevant for metrology. So it's jumping the gun a little bit, but I wanted to install this idea early on. Okay, so to start, I wanted to give an idea of why, in general, combining control and scalability might be challenging. And I might break this up into 2 categories. So there's one effect, which I would describe as classical noise. It's the fact that if I have more and more particles and I have to individually control, say, a laser that talks to a particular atom, I have many more degrees of freedom in my system that I need to control at a really high degree of fidelity. There's also quantum noise, which is the idea that if I have a quantum system, information about it might leak into the environment and take what was a pure state, a single quantum, a system in a single quantum state, and add entropy to it, so it becomes a statistical mixture or a density matrix. Despite these challenges, I wanted to highlight up front that there's really been amazing work in recent years getting to larger quantum systems in which we can have microscopic control and detection. So this picture on the left here is from Marcus Greiner's group, where they were studying antiferromagnetism in the Fermi-Hubbard model. This is a picture from the famous recent results from the Google supremacy experiments. And also there are a number of recent advancements in trapped ions and neutral atom tweezer experiments where we have these sort of designer quantum systems where we can control the interactions between the atoms and ions in this sort of tens of particle regime. Okay, so that suggests that we're getting better and better at combining control and scalability. I wanted to give a perspective on combining detection and scalability and the challenges and progress that we've made in that regard. So here's a picture from many different experiments around the world. 2 at the left and on the right here are from quantum gas microscopes experiments at Harvard and NPQ. In the middle here is a picture from John Bollinger's penning ion experiment at NIST. This basically is saying that we can look at a lot of individual particles pretty well. We sort of know how to do that in a lot of different systems. But another perspective that I think is quite relevant to have is how well can we measure these systems in an efficient way? And so what I mean by that is there are many different kinds of apparatuses with different cycle times. So for instance, on the left here, I'm showing a neutral atom experiment in a quantum gas microscope. On the right here is this trapped ion experiment that I was alluding to earlier. And this runs here is referring to how many times for the experiments from which these pictures come, how many times the experiments need to be run in order to get meaningful data. And if you have cycle times that range from a minute to 50 milliseconds, if you're running your experiments thousands of times, it's going to have real impacts on the kinds of things that you can measure. And I bring this up because many of the quantities that we might want to measure with microscopic observables, such as correlation functions and entanglement, those often depend on being able to measure our system many times. So being able to measure quickly is key. So this talk is really focusing on this technology of optical tweezers, which, as I'll argue in a moment, is really sort of this nice middle ground that combines many of these different design criteria that we think about in trying to scale to larger, more controlled systems. So the key idea for these tweezers is you have some microscope, that's this thing over here. You have tightly focused beams of light. And at these tightly focused beams of light, you can trap single atoms. So I'm showing here on the right pictures of single atoms in optical tweezers. And I'll flesh out what this really means in a little bit and how we take these images. And so the key point here is that this gives us a lot of control with a fairly simple apparatus. So what's more is that the optical tweezer platform in general really combines a number of key characteristics. So you have fast cycle times. You can scale to larger and larger systems, as we're seeing in many different experiments around the world. You have microscopic control and detection at a single particle level. You can rearrange the atoms to get to low entropies. And there are all kinds of different interactions that one might look at in these systems, ranging from Rydberg interactions to dipolar interactions associated with coupling to light, as well as contact interactions at short range. So at this top row here, I'm showing you a number of leading groups that have been doing this with alkali atoms. And actually in the bottom here is a picture from the experiments coming from the Knee group and Doyle groups, where they're actually now trapping molecules in optical tweezers, which really sort of illustrates the versatility of this platform. What also does is the fact that you can make things like Eiffel Towers with these systems, which this was something that came out of Antoine Brouwers's group in France. Okay, it's quite odd not being able to hear audience response, but I'll keep going. So because of all of the strengths associated with these systems and the things that they make possible, there have been a number of interesting experiments focusing on quantum information processing, such as in the Safman and Lukin group, as well as few to many body physics, where studies have been done in systems ranging from ground state neutral atoms to also long range interacting Rydberg systems. So what I'm going to be really focusing on today is the idea of studying alkaline-earth atoms in tweezers, which is a new atom as of only a couple of years ago for trapping, as a new atom that has been trapped by optical tweezers. And as I'll argue in a couple slides here, actually I think one slide, these open up a number of interesting directions. And I just want to be clear up front that I'm not alone, and my group is not alone in investigating this direction. There's been a lot of beautiful work coming out of Manuel Andres' group, Jeff Thompson's group, and actually, although there are no papers yet, there's a lot of cool things coming out of atom computing led by Ben Bloom. And these, I'm not going to have time in this talk to discuss all of these different results, but I just want to highlight there have been a number of advances in cooling, in detection, in different kinds of clock schemes, different kinds of gates, and even controlling different atoms with different quantum statistics like fermions. Okay, so why are alkaline earth atoms such a nice atom to work with? So they really offer a range of transitions for controlling and detecting the atoms. So for instance, there's this blue transition here at 461 nanometers that allows us to do fast, high resolution imaging of single atoms. There's this red transition, which is this narrow transition at 7.5 kilohertz that allows us to do high fidelity cooling and actually help with detecting single atoms in this blue transition. The clock transition is a very narrow transition in alkaline earth atoms that is actually one of the reasons why this species of atoms is quite famous, because it's key for doing optical frequency metrology. Another key aspect that I won't talk about today, but is actually a really interesting feature of these atoms, is the fact that for fermions, they have a nuclear degree of freedom that can be used as a qubit. So all of these different degrees of, all these different capabilities can be combined in interesting different ways. So for instance, combining this nuclear qubit with this narrow line transition can allow for site-resolved high fidelity detection of single qubits. There have been a number of proposals looking at new states of matter that might be detected at a single atom level when combining the nuclear spin degree of freedom and high resolution imaging. There have been new 2-qubit gate architectures that have been proposed for doing all kinds of different gates. And then finally, and this will be the focus of my talk today, there have been a number of clock architecture. There's a way of combining these different features for looking at new clock architectures. Okay, so that actually really will be the focus of my talk. And here are the things that I'm hoping to cover today. So first, I'm going to describe the platform that we have in our lab. Next, I'll describe our recent results of ours using this platform for looking at a tweezer clock. I'll then discuss recent results in which we've been able to reach high stability with these systems by working at much larger atom number. And then finally, I'll talk about an outlook in which we want to combine long-range interactions with this clock architecture to realize entangled optical clocks. One thing that I won't have time to discuss today is an idea that we're really pursuing as well in this apparatus, which is to look at Hubbard physics, where we use tweezers to prepare arbitrary systems in the optical lattice. Okay, so with that, I'll start with the quick overview of our platform. So on the left here, I'm showing you a picture of our apparatus and a CAD model of it actually. And this is nice because it highlights key pieces of it. So we have this microscope objective through which we shine light to make optical tweezers, and also with which we collect light to image single atoms. This microscope sits on a platform that's registered with a number of optics that allow us to have common mode registration of subwavelength potentials between the microscope and light controlled by these optics. So I'll come back to this later on in the talk. On the right here is an actual picture of the apparatus, and this blue dot in the center here is a strontium mott. What's key is that by overlapping light projected through our tweezer with a mott like this one, though a little bit colder, we can actually load single neutral atoms. So I wanted to take a slide or two just to talk about one of the nice versatile features of tweezers. So there are a number of different ways of making arrays of traps. But the key idea is that in our experiments, and the one that I'll be talking about today, we use a pair of acousto-optic devices, and all this means are deflectors, and all this means is that these are devices that allow us to tune the angle of light with an RF frequency, and we use some custom electronics out of JILA to do that. And these allow us to make large arrays like these ones pictured here inside of our vacuum chamber. One thing that we've been working on recently and has been pioneered in the groups out of France is to use an SLM, and this work has been done by a student in my lab, Felix Ronchen. And these are really cool devices. So they give you the ability to have control of really arbitrary geometries such as these that I'm showing here. And this is possible because you can control the wavefronts of the light that hits the SLM. And in principle, also flatten this wavefront so that you have very low aberration systems, and further make all the tweezers at a very similar power in the array. Okay, so once we project an array like this into our vacuum system, and if we have a cold cloud there, we can load single atoms and we can image them with very high spatial resolution. So this picture on the right here is showing that we can really distinguish the position of atoms and have an uncertainty in their position on the scale of 420 nanometers. We further can look at, distinguish whether or not there's an atom in our trap at very high fidelity. And there's been a lot of beautiful work coming out of the Andres group and the Thompson group really pushing on the number of nines with which we can do this. In our group, we can do this at the 99.9% level, where the losses are below a part in 1,000 in these systems. And this is just a nice feature associated with some of the transitions that are in alkaline-earth atoms. Okay, so one of the key things that we wanted to get to early with this apparatus was to be able to do ground state cooling of these systems. So the way we do this is by trapping the atoms in optical tweezers at a wavelength of 515 nanometers. This is really only relevant because it allows us to control the narrow cooling transition that I was referring to earlier to do ground state sideband cooling. I'm not going to talk about that too much today, but this data here just gives you a sense of what temperatures we can get to. To interpret these spectra, for example, this one on the right, you can think of this as basically this peak on the right here corresponds to driving a transition which adds a quantum of motion, or on the left here corresponds to a transition which removes a quantum of motion. The fact that we don't see this peak here on the left means that the atoms are in the ground state where this transition is no longer possible. And we can infer the temperature by looking at the asymmetry between these two peaks. And from this, we can say that we have a 3D ground state fraction of around 80% in 20 milliseconds with these systems. Okay, so as of around 2019 or so, with these systems, we had single particle detection, single particle isolation, tunable particle number, control of the atomic motion, namely the temperature of the atoms, and low dead time. Okay, so that's a quick summary of that. I think I'm going to keep going here, Shimon, and get to the next section and then take questions. With those capabilities in mind, I want to now discuss some of our work from last winter and summer, looking at a tweezer clock. So this requires some background, and I think it's useful to just give a perspective on what makes an atomic clock and how does it work. Well, a clock is given by having something that has very regular periodic motion, and we can track the passage of time based on the number of periods or cycles that we observe for that object that has periodic behavior. For an atom, we can do this, you can think of this in a couple different ways. So one is that there's a transition in the atom, and the light that's used to drive that transition has cycles associated with the electric field, and those cycles are the ones that we're counting. That's one perspective. Another perspective that's very equivalent is that if I induce coherence between the ground and excited state in an atom, that corresponds to some jiggling wave packet in the atom, and the cycle and those oscillations can be thought of as the oscillator that we're counting. So to make one of these atomic clocks, the key idea is I have some clock laser, it's locked to a cavity, but that cavity might have environmental perturbations associated with it that causes that cavity to slowly drift in time, and the atoms can serve as a reference on that slow drift. The key benchmark for how stable these systems can be depends on the quality factor and the number of atoms that you have in these systems, as well as something related to the duty cycle, and I'll come back to that later. So the key thing, and one of the reasons why optical clocks, namely atomic clocks based on optical transitions, have been so useful, is that they allow the use of effective quality factors that are very, very high because the transition frequency is so large. So for instance, at 1 second, a microwave transition might have a Q associated with it of 10 to the 10, whereas an optical transition will have 10 to the 15. And this underlies a lot of progress that has been occurring in the fractional frequency stability of these systems, excuse me. So this is a plot here from this nice review below, showing that in blue we have microwave clocks, and there's been rapid progress catching up to these systems using optical atomic clocks. And these precisions now that you can get with these systems are really quite amazing at the part in 10 to the 18 level. And so what this means is that you can have amazing measurements of things like gravitational redshifts that might be resolvable at 1 centimeter in 20 minutes, or you can look at geodesy or navigation and timekeeping. Redefinition of the second is being seriously considered for proposals that you might have observed on the archive, time variation of fundamental constants. There are a lot of important ideas. So the leading platforms for these systems have really been trapped ions and optical lattice clocks. And so these, just to quickly summarize them, one, the trapped ions are these pristine, idealized single clocks that can be interrogated at a high duty cycle and utilize all of the beautiful architecture that's in place for doing quantum logic with these systems. Optical lattice clocks, by contrast, operate with thousands of atoms using optical trapping of these atoms. And as I'll talk about, duty cycle can be relevant for how for the fraction of time that you can spend interrogating the sample. So the idea of developing a tweezer clock is really exploring the notion of whether there might be room between these two that balance the strengths of both of them. So coming back to this this picture I showed for how an optical atomic clock might work, there are really two key ideas that I want to convey for performance considerations for these systems. So one is this idea of stability, the precision that I accrue as a function of time, which depends on the quality factor, as I said before, and the number of atoms that you have that you can interrogate in parallel at any given run of your experiment. Another effect, which is talked about less often, but is super important, is this notion of the Dieck effect, which is the idea that even though my laser might be stabilized to this cavity, frequency noise scales on the, high frequency noise on the scale of 10 to 100 hertz can be aliased down into the time domain of your experiment and cause what would be a QPN limit or quantum projection noise limited stability to be slightly worse than this value. And so that's what this Dieck effect can come to do and how it might limit these experiments. So to place these two ideas in context, sorry, one more thing I want to say here. The degree to which this Dieck effect can be a problem depends exactly on the duty cycle of the experiment. So to place the different leading architectures for clocks sort of in the context of these two performance criteria that I was describing, going from trapped ions to three-dimensional optical lattice clocks is what OLC stands for, you have increasing atom number. So that means improvement with respect to quantum projection noise. Whereas going from right to left, you have increasing duty cycle and hence better resilience against Dieck effect noise. So in sort of early on in my time at JILA, when my group was just getting started, there were a number of really key results that sort of pushed at this idea of why some of the properties of optical tweezers might be useful for clocks. So one important result was out of the Ludlow group, which showed that for optical lattice clocks, really the Dieck effect can be so important that really what you want to do is perhaps make two of these clocks and interrogate them in an interleaved way so that you can reject entirely Dieck effect noise by having continuous operation. So this is really just saying the Dieck effect is super important. Another key result was showing that if you have single atoms per site, you can get to long interrogation times and coherence times for atoms in the sites of this lattice. And this is coming out of the Yi group at JILA. So the tweezer clock combines a lot of these useful features in a novel way. So you have single particle isolation. The spacing between the traps can be tunable, and I'll get at why that's relevant in a little bit. And you can scale the number of atoms from anywhere from, say, 5 atoms up to perhaps I think actually around 1,000. Furthermore, you can have high duty cycle operation in the system where you can image the atoms once, perform some sort of clock interrogation, and then image them again, and then recycle and do this over and over. So this allows you to get to very high duty cycles in the system. I'm sort of jumping the gun a little bit, but showing on the right here is that with this kind of architecture that is described, we were actually able to get to under half a millihertz line widths in these systems. So what was key to a lot of the progress that we were making was this really awesome clock light network that we have at JILA that is sort of nice to show. So there's this amazing laser that comes out of the Yi group, which we call the clock laser, and it's referenced to this football-looking thing called, which is a silicon crystal cavity. And light locked to this cavity can have a line width as low as about 8 millihertz. Importantly, this light can then be shuttled on a fiber over to the optical lattice clocks in the Yi lab, over to the Thomson lab where they do look at super radiant optical clocks, and then over to my lab as well. And on each of these fibers, we can do fiber noise cancellation to reduce what might be 100 hertz to a kilohertz of noise down to much lower levels that are near the fundamental line width of the laser. And this is really key both for clocks, but also for a lot of different ideas that are coming out in quantum information science. In addition to the key role that this plays for the work that I'll be describing, I want to highlight as well that this has really led to a lot of important discussions, key insights, and key contributions to the work that I'll be describing, and particularly by these people here, Eric Ulker, Will Milner, Ross Hudson, and Drew Kedar, and of course, June as well. So I'll try to litter key people who contributed to the work as I go along. So up front, one of the key things that we wanted to do was to make sure that we could get to long interrogation times for our atoms and tweezers. we wanted to do this because we were going to be operating at smaller atom number. Well, it was a balance between operating at smaller atom number or having long coherence times. And we thought that we could get the best stabilities by having a slightly smaller sample, but having long coherence times. And to get to that, there were key things that we had to consider. One was making sure that our atoms were ground state or as cold as possible. Two was that the tweezers needed to be interferometrically stable with respect to the light used to drive the clock transition. And finally, if we were going to be interrogating the atoms for a while, we need to make really sure that there weren't anomalous heating effects in our system that might really heat the atoms out of the trap or reduce their coherence with the light. So after really pushing on these different directions in our apparatus, we did Ramsey experiments in these systems, simply looking at a Ramsey fringe in this apparatus by doing 2π/2 pulses. And bear in mind that for these systems, we're working with 10 tweezers, so really on average about 5 atoms. So to get statistics, we have to run 50 times. So these were the results that were key to the paper that I was showing on a previous slide, where we could get to about 3 seconds of coherence time. And this was really within a factor of 2 or 3 of the state-of-the-art for atom-optical phase coherence. One of the things we really wanted to understand up front about this system was what was limiting the coherence. And so this is a plot here that's showing you that the Ramsey coherence performs differently depending on the depth of the tweezers. That's what the different colors here correspond to. Namely, for the deepest tweezers, our coherence time is shortest compared to the shallowest tweezers, in which the coherence time is longest. And while this isn't terribly surprising, since you might expect that the trap might perturb the transition, we were actually stumped for a bit at what was causing this. And eventually we figured out something quite remarkable, which was that really what was causing this was simply the fact that the different tweezers that we use to trap the atoms are at slightly different optical frequencies as a result of using AODs to prepare the traps. And even though this is on the scale of an extremely large detuning from transitions that are used to trap the atom, it can cause small shifts between the atoms in the sample. So this black line here is based on a prediction associated with that, and this dash gray line here is the sum of both this expected dephasing and the expected Raman scattering that we have in our trap. So this is really showing that we have a good sense of what was limiting us as we went to deeper and deeper traps. Further, we can use the fact that we can resolve single atoms and look at how the relative phase of the Ramsey fringe at each of these sites evolves differently as a result of this frequency difference among the traps. And so you can see here, starting from left at the bottom to the right, the slope of this line is changing, corresponding to a frequency difference between the traps. Okay, so one of the key things that I alluded to earlier was getting at the idea of getting to a very high duty cycle in these systems. So just to illustrate this notion, so this is a picture here of a Rabi spectra in these systems, actually operating at fairly low duty cycle of 22%, where we run 15 times and interrogate with a 30 millisecond pulse. And each time after we load our atoms, what we do is we image, we cool, and then we interrogate the clock transition, and then we repeat and do this, as I said, 15 times. Importantly, we can preserve the line widths that we have for single interrogations and as a result, get to larger duty cycles of these systems of up to 96%. So this really corresponds to, in the end, nearly 20 seconds of near continuous clock interrogation. And just because I don't want to sort of sell my group short, I just want to highlight that in each of these cycles, there's really a lot going on, ranging from changing magnetic fields, changing trap depths, all for the different imaging, cooling, and repumping stages that occur in the experiments. So getting this all down to a dead time of actually only 90 milliseconds was actually a big challenge for us. Okay, so a key benchmark for understanding the performance of a clock is the stability of the system, which tells you about how precision is accrued as a function of time. And so doing a free running comparison between the atoms and the laser coming from the JILA labs, we were able to see 4.7 times 10 to the minus 16. So if you don't have sort of context for clocks, to to compare to the state of the art, that's within a factor of 10 or about a factor of 10 away for what at that time was the state of the art. So a natural question to ask is, what number of atoms would we need to match this and what interrogation time? And the answer is 150 atoms and 300 tweezers and 2 seconds of interrogation. And I bring this up because later in the talk, I'm going to describe how we push towards those conditions. The second thing that I want to highlight before I move on is that these high duty cycles could be important for systems in which you're not operating with as good a cavity, but you want to have really low latency feedback on your clock laser. So I point this out because it's a relevant strength for these tweezer systems that we can go to these sub 100 millisecond dead times. The ion systems as well can go to low dead times too. Okay, so with that, Shimon, maybe I'll take a moment to take questions and also drink some tea.
So
Okay.
I want to remind all the participants to feel free to post questions in the Q&A, and we will read them. We have one question from Shimon. Shimon, would you like to ask your own question?
Sure. So Adam, could you say a little bit more about what actually limits the survival probability of the atoms when you read them out, and how many repetitions you could actually do of the clock before you have to start from the beginning and reload from a mott?
So the fundamental limit that we have in our apparatus for the detection is when imaging in 813 nanometer tweezers, it's essentially the vacuum lifetime. For some of the experiments, we push the imaging time to shorter times and hence the scattering rates to higher rates, which causes a little bit more loss than we could have in the 99.9% case. And that would also be a contribution to the loss that we have. So it's just a balance between which conditions we're optimizing for.
Okay, thanks. Let's see. Monica, do you want to read the question
sure.
we just got? Yeah.
Yeah, we have a question from Fabian Wolf. And the question was why the frequency of the tweezer light is crucial for ground state cooling.
Oh, that's a good question. So, so this narrow transition that I alluded to earlier, maybe I won't go back in my slides here. There's this narrow transition between the ground state of single dash 0 and the excited state triplet P1. These are optically separated states, which means that the light that we use can couple to those two states differently depending on the wavelength. Specifically meaning the trap depth for the excited state might be different than the trap depth for the ground state. So 515 nanometers is a wavelength where we can actually achieve a tunable so-called magic condition, which means that the ground state and the excited state are symmetrically trapped. That means that we can drive that transition with high fidelity and insensitive to the atom's motion.
Great. So let's see. One more question from Vikram Ramesh. Can you explain the sideband cooling concept once more? And maybe I will just add to that. I'm curious what limits the ground state fidelity that you achieve. That's my own.
Oh,
question.
yeah, sure. So so the technique that we use, I could have put more material in, but I was trying to just get quickly through the first part of the talk. Apologies for that. So we use a technique known as resolved sideband cooling. The idea there is you have light that is resonant with a transition that changes the internal degree of freedom of the atom, and at the same time reduces the motional quantum number of the atom. In doing that, if that transition has some line width, the atom will decay back down to the ground state. And if the trap is sufficiently confining, there's a low likelihood that the photon recoil associated with that decay changes the motional quantum number. What that means is that over that whole cycle that I just described, I've gone from an atom that's in the ground state in a particular motional state n, and it's now in that same internal degree of freedom, but now one level lower. So one way of thinking about this is basically entropy is leaking into the environment, and you're cooling the atom more and more down in the harmonic oscillator ladder. The limit on the cooling is given for this particular technique that we're doing is given by the ratio of the line width of the transition to the trap frequency. What actually limits our ability to spec a temperature is the resolution of our spectroscopy done in that transition.
Great. So we've got more questions coming in. I think I'll just give one more before you go on.
Sure.
So Dan Slichter asked in the YouTube feed, can you discuss some of the accuracy considerations in contrast to precision for tweezer clock arrays?
Oh, yeah, sure. And I'm actually going to come back to this in a little bit. But so let me be totally upfront. We have not done an accuracy study in this system, like a full accuracy study. So what we have shown so far is that these systems can serve as a relative reference on a laser. The key things that we'll need to consider for this system when we do a full accuracy study are both those that you normally would associate with an optical lattice clock with neutral atoms. So things like light shifts from the tweezers, BBR shifts from the finite temperature background. A unique thing that we'll need to consider is the effect of the tight focusing of the trap. The reason I bring this up is that a sort of interesting physical fact associated with tweezers is that the light, as it comes through the focus, actually so the electric field varies on the scale of a wavelength, which means that if you're slightly displaced to one side of the trap, you see a particular helicity of light that's opposite from what you see on the other side of the trap. So if an atom is moving around, it would see some average of that polarization that could perturb the transition and change its natural frequency. In the bosonic isotope, we don't expect that that's a big deal because you don't have any nuclear spin, but in the fermion, this could be an issue. And the fermion is also more resilient to other systematics, such as magnetic fields. And so it might be the best system to use for a tweezer clock, and we'll have to tackle understanding what the effect of these vector light shifts might be in that system. That was sort of a long-winded answer, but I wanted to be
great. So we've got even more questions, but we'll hold off on them for now and ask more at the end and let you continue.
Yeah. I might also run out of time a little bit here, but I'll keep going. Okay, so I'm now going to tell you about some recent results from our group. So this is looking at getting to really higher atom numbers and interrogation times in these systems. Okay, so around the sort of like last summer, basically, we were asking the question, how do we reach large samples while retaining control of the clock transition? And there's sort of a way of thinking about this that breaks down into two important criteria. So one, so we use these 813 nanometer tweezers to hold on to the atoms for doing the experiment that I was just describing, which is because it's very friendly to the clock transition. In fact, it's naturally magic with respect to the clock transition. The problem with 813 nanometers is that it has a polarizability that, for instance, is 3 times lower than what we have at 515. The power sources don't provide as much power. And the spot size that we get, like the waist, is also larger, which means the intensity of light that we get per unit of optical power that we put in our system is worse. So in that sense, it's actually less scalable. But actually, I meant to say this earlier, and I should highlight here, Manuel's group last fall was able to push this to a 40 atom regime with just purely 813 nanometer tweezers. So 515 nanometers are terrible for the clock transition because they massively shift. They very differently trap the ground state and the excited state, but they are scalable, and I say scalable in a loose sense, in the following way. I mean, you could make many traps with these systems, and on the left here is a picture of a 25 by 25 array average over many runs of our experiment. So on average here, we're trapping on the order of a couple hundred atoms. So what this suggests is that if we could combine these two in a particular way, we might be able to reach much larger system sizes. So that's exactly what we pursued. So what we worked on was basically having one 515 nanometer array in which we could do our cooling, detection, and loading, and then an 813 nanometer science array in which we could control the clock transition. One additional thing that we added in, which was sort of an independent but very important addition, was that we added an optical lattice along one direction of our tweezers so that we can trap the atoms more tightly along that weaker axis of the trap. So this is a picture of this full scheme. So these are, in the experiments that I'll be describing in a second, we can have a 16 by 20 array. This on the left here is a single shot of the experiment. On the right here is an average. Here I'm showing you that, without going into too much detail, we can actually measure the phase of the lattice wavefront and the pancakes that are imposed, and see that we can very precisely flatten that wavefront with respect to the tweezer array, which means we can uniformly trap all the tweezers in that array, all the atoms in the tweezers in that array. Okay, so then the key scheme that we do now is we have our science potential, and then we have this auxiliary potential defined by the tweezers and the lattice. We do our loading and imaging in the tweezers, we do ground state cooling in the lattice and the tweezers, and then we ramp both those guys off and load them into, and load the atoms into the science potential. So one thing that we were really happy to see was that with this system, we could get to low temperatures with just this cooling stage here. That's the black here. And the key thing to take away from all of these different plots is that this one, and this one is averaged over the whole array, and we can get to pretty low temperatures. On the right here, this is just showing that in the interior of the array, you might see that there's a little bit of bump here that affects our, that corresponds to some excitation of atoms from the ground state. But in the middle of the array, we don't actually see as much of that, and that's because the trapping is much more uniform there. Anyway, so the gray here corresponds to that you see behind the black. That corresponds to thermometry that we do after we load the atoms back into the original potential for detection. So this means that, from the 813 tweezers. So if we do a procedure of cooling, loading into 813, and then loading back. And this is showing that we're getting some heating, but not too much heating when we do that. And that's probably some technical limitation that we have in the handoff procedure. Okay, so the next thing that I wanted to point out is that in this system, we can do clock spectroscopy with 150 atoms, and do so with really pretty minimal variation in the clock transition frequency across the array. And we could do so to get to line widths of under a hertz, showing here on the top. Finally, another key thing is that we can have long lifetimes in these traps. So the black here is showing you the lifetime of a ground state atom, a singlet S0 atom in the trap. And the empty circles here correspond to the lifetime of the excited state of triplet P0, which is limited both by our vacuum lifetime and by scattering from the trap. Actually from both the light and also from black body excitation. And this minimum here corresponds to about 46 seconds. So that puts a benchmark on how long we can interrogate the transition for. So one thing I wanted to highlight at this point is that the lattice community, in particular a recent work from the Yi group, has really highlighted some important effects that can occur in neutral atom lattice clocks, in neutral atom clocks. So on the left here is a picture of the experiment that I'm going to be talking about in a second. This is a 3D optical lattice clock. And this work, which was spearheaded by Ross Hudson, looked at how the coherence of an atom, or the atoms in the lattice rather, depend on the lattice depth along a particular direction of the trap. And what they saw was that as they went to shallower depths, the coherence time got better and better, and this is because there's less scattering from the lattice. But then as they went to shallower traps, tunneling between sites of that lattice reduced the coherence time. So this is a really important observation that they made, and they have really clever ways to get around this in a next generation of lattice clock that will combine both large atom numbers and long coherence times. So one thing that I wanted to highlight about the tweezers is that they have the ability to change the spacing between the traps. So what that means is that we have independent control of tunneling both from the spacing and the depth. So that means that if we pull the traps far apart, we can also go to shallow depths where the scattering is less of an issue. A thing that's really interesting about our setup, and also I think highlights a nice feature of the tweezer clocks in general, which is that they serve as a nice way of studying neutral atom clock physics in general. And the example, the reason I think this is because of the following example, which is that, so in our setup, this optimum depth here, which this loss that we see would include the effects of tunneling, but the tunneling that we expect from we expect from the operating at that depth is about 1 hertz. So what that means is that disorder within the traps is pinning the atoms down, which suggests that that also could be a useful way in lattice systems to pin the atoms and reduce the effect of tunneling. Okay, so we wanted to do Ramsey experiments in the apparatus that I was describing, and one of the key things that about having larger atom number is that we could have a single run and get sufficient statistics. We didn't need to run many times to get an expectation value. And so here are data looking at Ramsey data. So this is the measured triplet p0 fraction as a function of Ramsey dark time. And what you can see here are blowouts of these different times. And I'm going to in a moment describe how to interpret these data. The important thing first is that this dark gray line corresponds to atom laser dephasing in our system. This lighter gray here corresponds to the expectation of dephasing from the different clock frequencies as a result of these light shifts that I was talking about earlier. And finally, this light gray here corresponds to loss of the excited state. What's important is that the variance of the data closely matches the expectation of the Ramsey, of the dephasing from the different clock frequencies. And so the way to think about this is that for these two plots over here, we're in a regime where there is atom laser coherence and there is also atom-atom coherence, meaning that the atoms have a well-defined relative phase. For these data here, we have we have minimal atom laser coherence, so the atoms are no longer well referenced to the phase of the laser. But the fact that this variance is large means that even though the block vector of the atom might be pointing in a random direction in the frame of the laser, if my atoms end up pointing along the y direction when my laser comes and rotates them along the x direction, I might get a large variance in my signal. Finally, at longer times, at 50 seconds, we have no atom laser coherence and no atom-atom coherence. So in this regime where we have good atom laser coherence and good atom-atom coherence, this suggests that we can access good relatives. We can look at the relative stability of our sample. What this means is that if we partition our sample and in terms of either, say, a checkerboard pattern like this or having diagonally in the array, we can look at how the expectation value of the excited state fraction plotted parametrically in one partition versus the other partition looks. And that gives us a measure of this variance that I was just describing. And importantly, there was a lot of pioneering work in atom interferometers and then also recent work in optical clocks looking at this exact kind of analysis and how to use it to extract the stability. So this plot on the left corresponds to a partitioning where there's actually on average 0 frequency difference between the different partitions in the array. On the right here corresponds to a partition where there's a net 7 millihertz difference between the partitions. And from these ellipse fits, we can actually extract that we observe a 7.15 millihertz difference with an uncertainty of 180 microhertz. I'm going to go a little bit quickly here just due to time. So one important criteria or behavior that one needs to study in these systems, particularly when doing this ellipse fitting protocol, is to understand to what extent you have biasing in your system of your relative frequency difference between the sides of your partitions in the array. What's important in that is that 0 phase difference, which in that phase is given by the size of the ellipse, the sensitivity of your system can look like it's better than it actually is. So this gray line here is a Monte Carlo simulation, which only has our observed Ramsey contrast in the simulation, and it agrees well with what we expect, and it's below the expected quantum projection noise, which is saying that there's a biasing in this effect because that physically can't happen. This red star here corresponds to a condition where there is a large phase shift between the sides of the array, and it's in agreement with the prediction of quantum projection noise, which is the solid red line. So this is really just meant to show that we were able to understand the various effects that influence our ability to understand the relative frequency precision of the partitions in our array. Doing this, we can then do an Allen deviation measurement and extract that we have a stability of 5.2 times 10 to the minus 17 per root tau. And then at the longest Allen deviation times, we can have a relative precision of 4.2 times 10 to the minus 19. So what this, I want to be clear what this means. This is saying that we can understand the relative frequency difference between one partition compared to the other at the 4.2 times 10 to the minus 19 level. Okay, so the present conclusions from these systems, and some of this gets at what I said earlier in response to Dennis Lichter's question. So with 150 atoms and the interrogation times that we can get to a relative atomic stability on par with the state of the art. The best that's been reported in lattice systems is 3 times 10 to the minus 17 per root tau. Accuracy studies are absolutely needed in these systems. We don't expect huge surprises, but this idea that I was describing earlier with the vector light shifts is really important to understand. And that's related to this thing I was saying earlier also about strontium-87. One point that I wanted to highlight about these systems is that they're really clean test beds for studying clock physics. So in addition to being an increasingly powerful platform for clocks in general, they're also just a nice way of studying what occurs in a clock-like system at a single particle level. Finally, the fact that we can have this many atoms and interrogate, for instance, the data I was showing you earlier was at 15 seconds of interrogation to get the atomic stability that I reported. This means that you could operate with, say, tens of atoms or 10 atoms and have second-long interrogations. Okay, so I'm going to go quickly through my outlook here. I think I have about 5 minutes. So as I alluded to at the beginning of the talk, one of the things that we really want to look at is trying to create entangled states on an optical clock transition. So we have this system where we can have stable clocks and long-lived excited states, which places a fundamental limit on the coherence times that we could have. And we can have versatile entanglement generation in these systems. So this is a plot from the Lucan group showing that it was possible to make a cat state between ground and Rydberg states. So one really beautiful thing to consider is whether you could do a similar kind of protocol, but map it onto an optical clock state so that then you could have an entangled optical clock with improved sensitivity. So to really get to these regimes, we really need to improve on the fidelity with which we can control the clock transition. I'm going to go through this somewhat quickly. This star here corresponds to the expected fidelity with which we can rotate atoms with the clock transition. And that's at about the 90% level actually for these data. And that's because the atoms are so are in such shallow traps that they're very susceptible to lambda key averaging of the Rabi frequency. So one thing that we've been doing is loading tweezers into an optical lattice potential where we can then have much higher confinement. So this is pretty preliminary data from actually a little bit ago now, where we have some initial image of our sample, and then we load into a lattice and actually image in the lattice. So the fidelity with which we could do this wasn't so great. It was 75% of the time at that time, but that actually was pretty good for our first go at this. So we're pretty optimistic that we can use this lattice and combined with the 813 combination with the 813 tweezers to improve our confinement. One nice thing that's cool about this is that if you look at the averaged images of the atoms imaged in the tweezers and the atoms imaged in the lattice, you can see that they're basically ending up where they started. It's not like we have some blur of atoms everywhere. So this is really suggestive that we're able to image atoms at single sites. Furthermore, we could actually do ground state cooling in these systems. Okay, so with that kind of additional confinement from the lattice, this could push our fidelities to much higher values in the sort of 99.9% regime. Okay, so I alluded to this fact that we want to generate entanglement on a Rydberg transition. And the way that we want to do that is by using the excited clock state and driving Rydberg transitions off resonantly. There was some beautiful work from the Andres group recently showing that doing this resonantly, you can get to very high fidelity gates between an excited state and a Rydberg atom. So this is really a summary of our status so far. We have a 1 watt UV system, which we had a lot of help with the NIST ion storage group to make. with the parameters that we expect to have in these systems, we can make many body spin models with kilohertz scale interactions and in arrays of varying geometry. So this could be useful for both clock physics, but also studies of, for instance, many-body frustration, the generation of cluster states, looking at excited dynamics in these systems. So this is a really interesting tool set in general. The key direction, or one of the key directions that we really want to look at in terms of clocks, is using these ideas that were developed in the Zoller group and based on ideas more generally of variational quantum eigensolvers to use a sequence of tunable gates on the system to promote better and better squeeze states. So what I'm showing here on the right is this sort of in broad strokes, the idea of using feedback on a gate protocol where the feedback signal is deduced from the amount of squeezing that we have. And the key point to take away from this is that if we add more and more layers of gates to the system, we can promote having more and more squeezing. So that's what's going from this blue to the orange here corresponds to the number of angles that we have to optimize in the gate sequences that we apply. Okay, before I close here, I just wanted to highlight two other projects that are going on at JILA and that I'm involved in. So one is an experiment in my group working with ytterbium atom arrays. And here we're really pushing towards having local 1 and 2 qubit control in an intermediate scale system. And we want to use ytterbium because this is a really nice way of getting to high Rabi frequency clock transitions with a well-controlled nuclear degree of freedom. And further, we want to use build-up cavities so that we can have really tight confinement in a lattice plus tweezers. Another experiment that's a collaboration with the Regal group is trying to put tweezer arrays in a cryogenic environment, which could be useful for a variety of different directions based on the technical advances associated with having a longer vacuum lifetime, a suppressed blackbody environment. One thing that we're exploring with Sewu and Rich Mirren at NIST is the idea of using integrated low noise cryogenic detectors. And finally, this kind of system would allow for flexible vacuum construction. Okay, with that, I'm going to close here. So I just wanted to highlight the people who were involved in the running the tweezer strontium experiment, and that is Nathan Schein, Will Eckner, Aaron Young, Matt Norcho, who's actually now at Innsbruck, and Ben Johnston, who was an undergrad in my group. And then further, I want to highlight Alec Jenkins and Joanna Liss, who are building this ytterbium experiment. Thank you.
Thanks, Adam. So we have some questions. Dan Stamper-Kern asks, what are the prospects of using the test of residual atom-atom coherence to test the limits of how much quantum coherence is possible to maintain over time and space, so as a fundamental test of quantum mechanics?
Yeah, this is a really cool question. So truth be told, we were actually thinking for a while about what kinds of tests that one can do using the fact that you can move the tweezers around and look at relativistic shifts in these systems. That would be an interesting thing because we could look at basically meters per second relative velocities. The challenge that we ran into in running the numbers on this was the fact that the tweezers are only moving by a small amount. So even though we could actually move them fairly quickly because they're tightly confined, the velocities that you could get to would be difficult. Shimon's group is doing amazing things towards that direction with much larger ensembles where this will be much more possible to do. In terms of actually placing fundamental bounds, it's a really interesting question. I don't immediately have ideas, but I would love to talk about it with you if you do.
Great. So let's see. We have a couple of questions about creating your arrays. So Gadi Afek asks, the advantages of an SLM are apparent, but can you name advantages of acousto-optic setup for creating the tweezers? And sure. Maybe I'll just, at the risk of saying too many things at once, there's a related question from Dima Budker, which is to say a bit more about how you drive the AOMs to generate the array.
Oh, yeah, sure. Okay, so to answer the first question, So the SLMs give you wavefront control, more arbitrary potentials. And that first thing I said means that you can make sort of really geometrically interesting things and correct aberrations in your system. The downside of SLMs are that the update rate can cause a flicker in your potential, which might change the shape of the potential, and also might cause a polarization rotation, which when transduced on a cube looks like an intensity fluctuation. So one thing that we're planning to look at in our system with that SLM is what heating rates we might expect, or what heating rates we observe at long times when holding in an SLM. The downsides of the AOD are that they're a bit less they're a bit less efficient compared to the SLM with respect to optical power, but they allow you to continuously tune the position of the atoms, which can be harder but not impossible to do in an SLM. So Dima Budker's question was about how we generate the RF to control the arrays. So this is with an FPGA that is programming a DAC. This DAC is then behaving like effectively a DDS system, which allows us to have independent phase, amplitude, and frequency control of many tones. And so our most recent version of this, which was really developed by someone in the JILA electronics shop, someone named Felix Weitmeier, allows us to have a single FPGA that's controlling 4 ports and allows for, I believe, 64 different frequencies to be controlled at the same time with very high resolution for the frequency, phase, and amplitude. I can actually send you exact statistics on that or specifications on that if you're interested.
Great. So Iris Kong asks, when you introduce the Rydberg interactions, will you need to add a rearrangement procedure to ensure unit filling? And if so, could you briefly describe your plan for that?
Yeah, that's a really good question. The answer is almost certainly. So it depends on what kind of experiment you want to do. This is something that given everything that's going on, obviously we're not working on it in the lab, but the programming of our experiment and this FPGA system allows us to do have the RF control needed to do rearrangement, and that's what we're planning to do. And the goal is to use either the 813 array generated with an AOD or the 813 array generated with an SLM to hold the atoms and then do rearrangement in that system with the 515 tweezers, where we would go row by row and compress the array. Actually, there was one other question. I'm sorry. What was that?
I think you addressed the question.
Oh, okay. I thought there were maybe 2. Okay. Yeah. Oh no, there was one more. Like, what's the effect of having a disordered array for doing entanglement in a Rydberg clock system? So Nathan Shine, the lead postdoc on that experiment now, has been doing calculations looking at how that might affect things like correlators and squeezing. And also actually in that paper that I was citing earlier out of the Zoller group, they've also looked at the effect of disorder. And for instance, in that gate scheme where you optimize with respect to the angles of the gate, for a fixed arrangement of the atoms, meaning that you'd have to image the same configuration many times, you couldn't start over, you could optimize that sample. So it's robust against the ordering, but you need to be in a regime where you hold on to the same atoms, which is an important limitation.
Great. So we'll take one last question from Ivan Deutsch, who asks, can you say more about the details of the Rydberg dressing and how well do you expect to achieve the entanglement for a given detuning and Rabi frequency?
So I would say that this is a sort of hard question to answer at the level, in the sense that really we just need to, right when everything closed down, we actually had Rydberg light on the atoms and could see the line. But really understanding how well it's going to work is just going to depend on tons of technical details associated with the experiment, which are the kinds of things you, Ivan, are really good at understanding and studying. So we should certainly talk about that, particularly in the context of this kind of Rydberg dressing protocol when you're going from a single photon optically excited state.
Great. So with that, I think we're out of time. So let's just thank Adam one more time for a wonderful talk.
Thanks for a great talk, Adam.